In this video, we will be looking at the sequence where the nth term, an, is defined by 5 minus n times 2 to the negative n power. The first thing we will do in part A is to list the first 5 terms of the sequence. When I say the first 5 terms, that means the value n is going to take on the value 1, then the value 2, then 3, then 4, then 5. We call n the index. We can relate this notation to f of x equals 5 minus x 2 to the negative x power. So if we write f of 1, we plug in the number 1 every place we see the value x. In just the same way, if an is 5 minus n times 2 to the negative n power, and we want to find a sub 1, then we plug in the number 1 in every place we see an n. So a sub 1 is 5 minus 1/2, which is 9/2, or 4.5. That's our first term. Our second term is a sub 2. A sub 2 is 5 minus 2 times 2 to the negative 2 power, or 5 minus 2 divided by 2 squared, which is 5 minus 1/2, or 9/2, which again is 4.5. A sub 3, I replace all the n's by the number 3. 5 minus 3 times 2 to the negative 3rd power is 5 minus 3 divided by 2 to the 3rd power, or 5 minus 3/8, which is 37/8, or 4.625 overall. A sub 4, I replace all the n's by the number 4. We have 5 minus 4 times 2 to the negative 4th power, which is 5 minus 4 divided by 2 to the 4th power, which is 5 minus 1/4, which is 19/4, or 4.75. One more term right now. A sub 5 is 5 minus 5 times 2 to the negative 5th power, which is 5 minus 5 divided by 2 to the 5th power, or 5 minus 5/32, which is 155 over 32, or 4.8435. So the first 5 terms of our sequence are 4.5, 4.5, 4.625, 4.75, and 4.84375. I want to point out that even though we only found the first 5 terms of this sequence, we could keep going as long as we wanted. Just keep plugging in larger and larger integers for the number n. In part B, we want to determine whether the sequence is increasing, decreasing, or not monotonic. If we look at the first 5 terms, we have a fairly good guess that our sequence is increasing. At least it appears so from the first 5 terms. One way to determine for sure whether the sequence is increasing is to look at the associated function. So we'll look at the function f of x equals 5 minus x times 2 to the power negative x. Notice that what I've done is I've taken the term a sub n and replaced all the variable n by the variable x. However, this helps because we know that this function is continuous. Because this function is continuous, we can try to take the derivative. Okay, so f prime of x is 0 minus, and here we'll use the product rule, x times negative 2 to the negative x times natural log 2 plus 2 to the negative x. And we can factor out negative 2 to the negative x. So we have 2 to the negative x times x natural log 2 minus 1. Now the derivative equals 0 when either 2 to the negative x equals 0 or x natural log 2 minus 1 equals 0. The first equation has no solution. The second equation is true when x equals 1 over natural log of 2, which is about 1.44. So we know that the derivative is 0 only when x is about 1.44. So if x is greater than 1 over natural log 2, then we know x times natural log 2 minus 1 is greater than 0. Because 2 to the negative x is always positive, we know 2 to the negative x times x natural log 2 minus 1 is greater than 0. So that means that f prime of x is greater than 0. Remember that a positive derivative means that f is an increasing function on the interval from 1 over natural log 2 to infinity. Well, because f is increasing, that means our sequence a sub n is increasing for n greater than 1 over natural log 2. Now n has to be an integer, so that means rather than saying for n greater than 1 over natural log 2, we might say for n greater than or equal to 2. But remember, we found the first 5 terms, and we know that the first term and the second term happen to be exactly the same. So even this n greater than or equal to 2 is not very important. For part C of this problem, we will determine whether this sequence is bounded. I want to notice, because our sequence is increasing, we know that a1 is less than or equal to a2, is less than or equal to a3, is less than or equal to a4, and so on and so on. And a1 is 4.5, we calculated in part A. So this means that 4.5 is less than or equal to a sub n for all n. Or in other words, the sequence a sub n is bounded below. Now I'd like to look at the term a sub n. A sub n is 5 minus n times 2 to the negative n power. Well, since we can assume that n is greater than or equal to 0, we know that n times 2 to the negative n is greater than or equal to 0. Well, multiplying by negative 1 on both sides, we know that negative n times 2 to the negative n power is less than or equal to 0. And adding 5 tells us that 5 minus n times 2 to the negative n is less than or equal to 5. Well, this is our formula for a sub n. A sub n is less than or equal to 5. This tells us that a sub n is bounded above. if I put this all together, we see that each term, a sub n, is between 4.5 and 5. So a sub n is a bounded sequence. All of the terms in the sequence fall within the range between 4.5 and 5. Now, this is not officially part of the problem, but I do want to point out that we have determined that a sub n is bounded, we just did that, and it's monotonic. We did that in part B when we showed that it was increasing. So by the monotonic sequence theorem, the sequence a sub n converges. In other words, the limit as n approaches infinity of a sub n exists. We could go on and find that if we wanted to. I will let you know that the answer is 5. You can work on that on your own if you like.